Yeah, welcome to the lecture course on quantum gravity. After a lot of preparation last time when we treated the Hamiltonian formalism of general relativity, we now come to the Hamiltonian quantization. So I had in chapter 2 the quantization in the part with the path integral, and now we do it with the Hamiltonian formalism. So this is actually split in two parts. So today I will make the general formalism and general properties. The next week I'm not here. No, I'm at a conference, but I hope you will nevertheless come because Tadevik will give you an interesting topic to hear about relational systems, which is from the chapter 3-4 of the book, but without recording. But so you cannot listen to it in the evening, so you should come here. And then in 2 weeks, I will present the second part of chapter 5, which is a semi-classical approximation, which is important for two reasons. First, I mean, I worked on that for many years. And second, I think that's the approximation where you can see how the standard time and also relativity emerges at least in some limit from quantum gravity. So it would give you, or it gives you the connection between the quantum theory, the full quantum theory, and Einstein's theory. So we call it quantum geometrodynamics. Geometrodynamics refers to Einstein's theory in the standard variables, which is the metric, or canonically thinking the three-dimensional metric and the second fundamental form. And quantum, of course, is then the quantum version of that. In chapter 6, which will be then in 3 weeks, I think, I will present again a Hamiltonian formalism of relativity, but in different variables. And this is called loop quantum gravity, which is a variant of the canonical approach that is younger than this one and has some other aspects. Now, first, let me say something about the general program of this. Of course, quantization, as you know, is something heuristic. We cannot derive, I mean, from first principles, a quantum theory. So what we know is the classical limit. The classical theory is the classical limit. And we somehow have from this, by heuristic means, somehow to construct and to guess a quantum theory that, first has to give back the classical theory in a consistent limit, and second, has to be tested experimentally. This is what we did with quantum mechanics. Now here, what we do is we follow the prescription that Dirac generally gave us for quantizing system with constraint. So if you have a classical constraint, which I write here in the form GA in Dirac notation as vanishes at a constraint. So for example, Gauss' law in electrodynamics, or last time we had Hamiltonian and momentum constraints in relativity. Then you say, this depends on some variables. We make them into operators. So we have an operator version of that. Okay, this is non-trivial, of course. And this has to be applied on a wave function or the function null, and this gives 0. No? So that's a prescription, and it's the idea is to have a quantum version of this. So if you have such an equation, then you would definitely conclude that any expectation values of this is also 0, and from this you would in the classical limit conclude that this. Okay, so that's of course first now a wish or a desire to do, and one can separate the steps to do that in the following 5 or 6 steps. So the first thing is to answer the question, what are the fundamental variables? Fundamental variables. So, or in loosely speaking, what are the P's and Q's? Now, you know from quantum mechanics, P and Q are canonical conjugate. It's not Q and Q dot or something, it's P and Q. They obey Heisenberg's commutation relations. And this is at the center of the quantum mechanics. It gives rise to the uncertainty relation and all that. So what are the P's and Q's? The Q's and P's. So if okay, here they are two, but if you, of course you have maybe in higher dimensions and so have various of them. So if we denote if vi are these variables, then I mean you would demand the following. So if classically you have a variable v3, which is the Poisson bracket of v1 and v2, say, and then quantization would mean you transform this into an operator equation which looks like that. So like in quantum mechanics is, of course, I mean, plays the role of what to follow here. So you have now the commutator between these, and you put in the h bar and the imaginary unit, like with Heisenberg, and then you get this. For example, here we will have HAB, the 3 metric, and the momentum, which we had last time. For completeness, also we take here the 1 in addition, unit operator. So this is what we do here in chapter 5. And then in loop quantum gravity, or what is called Ashtekars variable, so we have here instead of this a connection and a conjugate quantity, which is a generalized electric field, and one, or you can integrate them over a line. This you will learn in chapter 6, so it's just an outlook. What is called a Wilson loop around the loop, and the canonical conjugated variable is a flux through that loop. You can imagine this as a kind of flux of an electric field type variable. So this Fi is just a test function. So this we treat in chapter 6. So you will learn that, or you can have, of course, other variables. Maybe you have your own choice of variables that classically reproduce relativity, but that in the quantum theory do something else. Yeah. So here, of course, this is what we do here. This is what we do here. So it means that this is plays the role of our Q's. I mean, there are various of them, and here this is plays the role of the P's. So they are the conjugate variables. So we have here H A B hat of X and P C D hat of Y is I H bar, and then you have deltas for the discrete indices, and you have the delta function for the continuous indices, because this depends on space points. So this has in fact infinitely many indices, if you like, because in space of course you have infinitely many points, and then you have here this AB goes from 1 to 3. Yeah? So this corresponds to QP is IH bar in quantum mechanics. Now the second step addresses the quantization of a general variable, not just the fundamental variables, but a general variable that is a function of P and Q. Can you also impose this rule? Now let us look into an old textbook, the one by Dirac, and he writes, let me quote him, the strong analogy between the quantum boson bracket and the classical boson bracket. Okay, the quantum boson bracket is what he means with commutators, but he invented this in the 1920s, this analogy, or that you should, or this rule from boson bracket to commutators. Now, while he was walking near Cambridge, he had this idea, as he himself recalls. Okay, this strong analogy between the quantum boson bracket and the classical boson bracket leads us to make the assumption that the quantum boson brackets, now comes an important small part, or at any rate the simpler ones of them, have the same values as the corresponding classical boson bracket. The simplest boson brackets are those involving the canonical coordinates and momenta themselves, so the P and Q. And in fact, he was very careful when writing, or at any rate the simpler ones of them, because in general we cannot do that. Yeah, so maybe I start here. So quantization of an arbitrary variable so if you have, and let me use directly this case. I mean, this is general, but let me immediately restrict to quantum general relativity. So if I have any function that it depends on the 3 metric and its momentum, then, I mean, how can I construct the operator out of it? Now, there's a theorem in quantum mechanics going back to Grunewald and Van Hove, 1946, 1951, that says, okay, this cannot be obtained without violating the rule here, without violating this rule. Well, let me call it star. So there is a theorem, Grunewald, Van Hove, 1946 and 51, so this independent work cannot be achieved without violating star. Okay, this of course gives a blow to this general program, but it means that quantum theory has many more options than just maybe putting hats on on the fundamental variables and F, because it has to do with the issue of factor ordering. That, I mean, in the quantum theory, factor orderings, they are not given. I mean, you will have to choose them, because classically you have functions that always commute. So you cannot somehow expect that you can simply realize this by, I mean, just putting hats. So you cannot achieve that in general. So you must have must bring in some additional criteria to get it. So this is what Dirac seemed to have anticipated by writing, or I mean the simpler ones of them, which are the canonical ones. Those you make into commutators, but you cannot just have, say, any function, classical, and another function in the Poisson bracket, and assume that then the commutator just follows by these rules. It can be in some cases, it can be for some, and if you do it for some, for others it will fail. So the statement is you cannot do it for all possible functions. It's not that if this holds, you can do then for any classical functions the Poisson bracket translate into operators. This will lead to inconsistencies in general. That's what this theorem tells. Okay, so this means we have to be careful here and focus here on that here. So we go on with that. And you know, from quantum mechanics, we have to implement these relations on some representation space, which will then be a Hilbert space in quantum mechanics. So the question is whether we can also do this here. No? So we represent the operators in some space, representation space. So, and we choose here the so-called functional Schrödinger picture because it's a Hamiltonian formalism, so we talk about wave functions. So we have here the functional Schrödinger picture. Functional means that instead of, say, in quantum mechanics, you have here h bar over I, just derivatives of vector q, you have here now the functional derivatives. Because here these are functions, no? Because they depend on x. So we have here for geometrodynamics HAB operator of x. I just write here x, but I mean here x1, x2, x3. I hope that's acceptable just for writing simplicity. And so this depends on HAB then of x. It's just a multiplication. No, this is like the Q operator in quantum mechanics. You implement by multiplication. And the P operator by differentiation. So P C D of x on psi of HAB of x is h bar over I d over d h c d of x psi of h a b of x. So that means functional Schrödinger picture, you have the functional derivatives instead of just a d over dq. But this should, in spite of now this for relativity, should look familiar to you, because this is how you learn typically quantum mechanics. Now the psi here, okay, where is the psi defined? It's here in the quantum gravity. Okay, we start with some representation space that is not yet necessarily a Hilbert space. It will become clear soon. So we call this an auxiliary space, ein Hilfsraum. Of course, it should be linear, but not yet necessarily a Hilbert space. Why is this open? Because the constraints are not yet implemented. I mean, in quantum mechanics, you don't have these constraints here. So you just have everything is there in your representation space, and then you just have one space, and one presents then the argument that this is an Hilbert space because of the probability interpretation. But here, we think that only solutions to these equations make sense. So if you start with general psi's, not necessarily solutions, then of course you do not really need to impose here already the Hilbert space. So we have to do this in the next step 4. So the implementation of the constraints. And here we have, I mean, this is the general situation, but here we have H orthogonal on psi equals 0 and HA on psi equals 0. Recall last time we had these 4 local constraints, the Hamiltonian constraint, momentum constraint. We got this by this 3+1 decomposition. And they are constraints in this classical sense. So when we quantize, we write it in this form. Often you find in the literature, because physicists like to save writing space and writing effort, just to one equation h mu on psi equals 0, where mu is this one, and the A, this is 1, 2, 3. So don't be disturbed if you find this notation is just to condense this into one formula. Now let us assume we have solutions to this. So we have a solution space, which is a subspace of this full space, and we call it F0. Okay, now the solution space, it's not yet clear that this is the final space, because you would expect other constraints to that space, like normalizability. No? In quantum mechanics, also you have normalizability because of the probability interpretation. So further restrictions lead then to assume that we have, say, that a physical space, I call it F physical, is of course part of this solution space. Solution space may have maybe exponentially increasing wave functions or whatever, which of course is in this original auxiliary space. Okay, now this solution space, this is largely an open issue, and I will discuss the options that we have here for that. So another issue is then the role of observables. Now, observables, unfortunately, is something in the literature that is not uniquely defined. Is it something like in quantum mechanics we call everything that we can describe by self-adjoint operators as observables, or something that you can observe in a operationalistic way, say with rods and clocks and in the laboratory? I mean, in quantum mechanics you call everything observable that is described by operators, but if it's complicated you cannot directly measure it. Now in gauge theories, Eich theory in gauge theories, there's another meaning, a third meaning of observables, namely those quantities that are gauge invariant. For example, if you think about electrodynamics, the original formulation has E and B fields, but you can also have a formulation with the gauge potential A. Now A has this gauge non-invariance. No? So if you have make a gauge transformation, A goes to A plus a gradient. But E and B are gauge invariant, so they are observables. But A is not. And so you could also impose this here. Observable would mean, in a sense, perhaps commuting with the constraint. The constraint generates these gauge transformations, and the constraint then classically with the Poisson bracket would be 0, and in the quantum theory would lead to a vanishing operator. At least it seems so. Yeah, it will not be exactly like that. So if G is the gauge generator, then an observable would be something that classically under gauge generation does not change. Yeah, for example, if you put in here Gauss' law or something for electrodynamics, and here, or in the quantum theory, you would then have, say, O G equal to 0. Now, what is here the gauge generator? Now, here we have these constraints, H orthogonal and an H. So people have for some time believed that observables are such that they should commute with these constraints. Because you think about, say, the Gauss law and other cases that had nothing to do with space-time, where you have gauge transformation, and so things should not change under gauge transformation. But that would lead to some puzzling results, especially for this here, because this is the normal deformation, the important part of the Hamiltonian. So if this commutes with the observables, it would mean that observables are constants of motion. So, because the Hamiltonian is also a sum of these, and if everything commutes with the Hamiltonian, there is no change. So you wonder why you are here, no? And why you will live if the world is, if only things are observable that do not change. So that cannot really be true. Of course, you can call it observable, but it's not an observable in the sense of gauge interaction. So actually, what one has to do, and I'm afraid that lack of time forbids me to give you a lengthy discussion of this, which is very interesting, but has led to much confusion in the literature, and so I would need much more time to do that. It's in the book, of course, but I would only tell you, what comes out. And the point is that we call observable only those things that are invariant if you have here a certain combination of the constraints, and also of what I called last time the primary constraints, which are the ones that have to do with the vanishing momenta of lapse and shift. So here observables are quantities that commute with the full, I call it gauge generator of a general relativity, so including the h mu, classical or quantum, and the primary constraints which I so momenta conjugate to lapse and shift vanish. Now, and the reason is that, why do you need these things? The reason is that we talk here about space-time, not about some internal symmetry. And for space-time, we have the full metric, and the metric consists of the 3 metric and lapse and shift. Lapse and shift, all of this together, these are 10 variables of the 4-dimensional metric. So if you want to have Einstein's or the diffeomorphism invariance of Einstein's theory, you have to include them. And one can show that if you do that, then you can relate this back to the old coordinate invariance and diffeomorphism invariance of Einstein's theory. And it's not the case that only constants of motion are observable. So it's not the case that only those things are relevant that commute separately with this. As you find in the literature many such statements. And it's evident that constants of motion alone would be much too restrictive to call observables. Yeah, so that's a very short summary of a long story that I think only in the last 10 years or so in the literature was clarified. So before that, you had paper 1 and paper 2 and paper 3, and you got different results from this. And for example, some people have argued, in the 1990s, that, okay, this here by themselves, these are the momentum constraint, this observables should commute with this, because this is just 3-dimensional coordinate transformation. But not this here. And for example, Karel Kuhasch has then stated that those things that commute with everything, they should be called perennials instead of observables. Perennials, in German, that's so immerwährende. So these are the ones that never change. Okay, perhaps we come back to that if needed. But if you have a question at that point, then don't hesitate to ask. It's a subtle issue, but I think it can be understood and solved. My opinion. Okay, so we have this the fundamental variables, we have the constraints, we have the solution space, and probably a much smaller space after imposing normalizability. Now, the question is, of course, about whether we need a Hilbert space. This is your daily bread in quantum mechanics, right? This you have learned from the very beginning. And this question has also to do with, the role of time. Role of time in the quantum theory and, okay, here in quantum gravity. Why? In quantum mechanics, we have an external non-dynamical time parameter t, as you know. But in GR, we have a dynamical space-time. Time is part of space-time. It's not separate. It's only space-time has significance, and it's dynamical. Gravitational waves that I emit here when gesticulating here, they change the clock running here in the room, right? So this is not an external parameter. You will not notice, and if you will notice something, it's not due to my emission of gravitational waves. But you see, this is in conflict. Now, in quantum mechanics, you have the Schrödinger equation. Now, and you have here this first derivative with t. We have seen in section 3.1 that if you have the parameterized particle, that this comes from this constraint pt plus h equals 0, so that this momentum is linear. And but you see here, this t comes together here with this IH bar, also with this here. So if that were not a first derivative, then you would not have the I. So this complex nature of the wave function comes from this first order time derivative. If you had a pt squared as a constraint, you would get a minus d squared dt squared. Now, okay, so you have here complex wave functions. Complex wave function, and you know, of course, that this is very central for quantum mechanics because of all the interference effects and everything when you're phases. Now, why are wave functions complex? Why do they need to be complex? So at the beginning of quantum mechanics, of course, this was heavily discussed. So there is a famous paper by Ehrenfest über einige die Quantenmechanik betreffende Erkundigungsfragen. So on some questions concerning quantum mechanics, where he has many, about 1930, many questions among the question why complex wave function. And then Wolfgang Pauli responded to these questions. And so Pauli in 1933, he had a paper where he answered the Ehrenfest question. He said, concerning the complex nature, it's because of the probability interpretation and because of conservation of probability. So he had, so if you have a wave function in configuration space, so this object here, this is conserved in time. And he showed that if the psi's were only real, then you could not, at least not write something easy, an easy expression down, because you would have sines and cosines and everything. So this would not just be easily conserved in time, and not like this simple expression. Well, he even shows it that it must be that if this expression should not contain time derivatives of psi. So if you have something like this conserved in time, then wave function should be complex. So this is conservation of probability, of course. So this complex nature and the structure of this Schrödinger equation has to do with the possibility to easily write down such an expression, implementing Bond's rule, Bond's probability interpretation. So the question, of course, is if we will no longer have such an equation, do we need also this? So it seems also that this is really tied to the external time. The conservation of probability means conservation in time t, and this is the external time that is not changed. But if we don't have an external absolute time, do we need this? This is one of the questions. Now, concerning the time problem in quantum gravity, where we have these constraints, but not a Schrödinger equation, there are different attitudes to what people call the problem of time. It's not clear whether it's really a problem. I mean, it's a feature of this equation that we understand why it must be like that. But it's in the literature often called problem of time. And okay, there is a classical problem of time, which is not the issue here. The classical problem is that space-time is dynamical, so you don't have a background. That's already in Einstein's theory. There is not a background. And then, of course, there's the quantum version of that. What happens when we quantize? And so people in the literature, and especially Isham and Kuchash, which I also cite, so Isham and Kuchash, they distinguish between three options. I mean, they say, okay, we could try to establish a concept of time before we quantize, something distinguished that at least substitutes Newtonian time. It's not Newtonian time, but it's substitute. Or we first quantize and then try to identify a concept of time for the quantum equations. Or we restrict to timeless options. I mean, just without time, t, and time only emerges semi-classically. This is what we do in 2 weeks. There we see that whatever happens at the full level, we can understand in which limit time at least approximately emerges. Approximately. That's all we need for our everyday physics. So here we can have a choice of a concept of time before quantization, or B, choice of a concept of time after quantization, or timeless options. Okay. In a sense, these are options saying that only the semi-classical time exists. So only semi-classical time exists. Okay, this we will do in 2 weeks here, and today we will focus on A and B. Okay, so first A. So A is, okay, I don't write it down again, choice of a concept of time before quantization. And that's an attempt to deparameterize classically the theory as much as possible. Now, deparameterization, you remember from chapter 3, we discussed parameterized theories, the simplest, the parameterized particle. And then we found the constraint pt plus h is 0, and we could deparameterize it by choosing t, the standard Newtonian time, and solving the constraints. Now the question is whether we can deparameterize the constraints of relativity. The classical versions of this, whether we can deparameterize it. unfortunately, there's a theorem that at least forbids it globally. I mean, in all of configuration space. So can GR be deparameterized? I mean, then you could identify some time, no? Like here the PT plus age equals 0 can be deparameterized. Okay, the answer is no. I mean, there's often a paper cited by Charles Thorer of 1993 where this is shown. But this only shows that it's not globally possible. I mean, it does not exclude a possibility that you can go in phase space where you are classically to some region and do it there. And maybe in other region it's something different. So at least not globally. At least not globally. So locally it's possible, and of course there are examples, there are models where you can do that. And in particular, Karel Kuchasz, who worked a lot on canonical quantum gravity, is one of these proponents of reduced quantization, and he has tried over many years to discuss situations where you can deparameterize it, where you can reintroduce a concept of time. So I will briefly review this and then show you that this leads to many problems, which is why we now have follow the opinion that this is not a general strategy, that you can certainly in particular examples do that, and then also it gives you insights, but not for the full general quantum general relativity. But it's instructive, no? And it's also what the many people thought should be done in the first place at the beginning, no? But the reason why people want to do is, of course, this conservative attitude to go back, I mean, to a Schrödinger type equation. Okay, now what would you like to do? Okay, you have here the 3 metric and its momentum. So the canonical variables, the Q's and P's, and you want to make classically a canonical transformation, which does not change the Poisson brackets. And in 2, these are 6 and these are 6. I should always write, of course, per space point, 6 times. Some people write 6 times infinity cube. If you like that notation, you can use it, but I think it's clear that these are 6 local and these are 6 local degrees of freedom. So to make a canonical transformation, and there are the following. Okay, this is just a notation. Well, I should write here everywhere x ps x. So and this indices capital A and B. So these are 4, and these are 4, and these are 2, and these are 2. No? So you somehow decompose this 12 into 8 plus 4, or if you just restrict to the Q's, this 6 into 4 plus 2. And these are called the embedding variables. They would, in the language of chapter 3, describe the embedding of the 3-dimensional hypersurfaces in space-time, just a pure embedding, kinematics only. And this would then be the physical, the dynamical variables, which are 2. No? So if you think about, say, weak gravitational waves, then you would think, how do I find them here in this formalism? I can make such a transformation, and this just describes me how I put my hypersurface, and the remaining degrees of freedom of gravitational field are dynamical. These are 2. This would correspond to the gravitons, no? To the two massless gravitons, or the 2 helicity states of the classical gravitational waves. No? So this would be then the embedding variables. Embedding variables, and this would then be the physical degrees of freedom. Okay, this looks very nice. Yeah? If you see that, okay, why not do that? Because everything in HAB and PCD is mixed, and how do we find gravitons and the like? But if we can separate this description just of kinematics from the dynamics, then I think we know what the physical degrees of freedom are. Okay, but how do we do that? I mean, classically, we have these constraints. Okay, classical constraints. And yeah, if I have here, okay, H orthogonal to 0, HA to 0. So those should then be solved, say, with respect to some momenta, like in the parameterized particle, so where we have Pt plus H equals 0, and some rest, so that we also can write down Pb plus some rest is equal to 0. So solve them in the form some Pa of x plus the rest I call small h a depending on x, and depending on the rest xb phi r ps equals 0. Yeah, this notation here means this thesis that this is just a function on x, but it's a functional on these because they all here depend on x. Yeah. No, it looks more complicated, but perhaps you, or I hope you understand what is the purpose of this. No? To write a constraint in such a form that you can quantize it a la Schrödinger, so that you have a linear momentum and the rest. No? So this here, compare this to what we have, Pt plus H is equal to 0 for the parameterized particle. No? So that would correspond here to this, and this would then be the reduced Hamiltonian. No longer a constraint. The constraint is the total thing, but the physical non-vanishing Hamiltonian. So if you could do that, then you could insert this. So I continue here into the action. So action would still classical everything. dt d3x pa xa dot plus pr phi r dot minus n h orthogonal minus n h. Yeah, no? So these are all. This is pq dot minus h, and so these are the embeddings, the physical ones, and of course you have to add the constraints. Now, if you use the constraints, then you would set this to 0. Because you have then solved it, and then you would have to use this equation. So you would here substitute this PA by minus HA. Then you have somehow deparameterized it, or tried to do it. So you have here the integral d3x PR phi r dot. So that's this term. And then you only have here, because this is 0 and this is minus HA of x, xb phi r ps. Okay, xa dot. So that would be the deparameterized form. And this here, and this here, they are now prescribed functions only of t and x. So they are not, we do not vary with respect to them. So here, these are prescribed functions, of t and x, not to be varied. So then you would have then you're left. If so, this program, I think, of course, formally I can write this down. If this program were to succeed, then I would end up with a system without constraint and a usual non-vanishing Hamiltonian called a true Hamiltonian, describing the energy. No? So then you would arrive at a system without constraints and with a true Hamiltonian HA or integral over HA, true Hamiltonian H true would then be integral over the three-dimensional hypersurfaces d3x, HA, this is the Hamiltonian density, of course, xb t phi ps xa. So I add here this t to indicate that these are classical functions that are prescribed. No? Out of this you get then the Hamilton equations of motion, like in mechanics. Yeah? Q dot is dh over dp and p dot is minus dh over dq. But you must keep in mind that in contrast to classical mechanics, there is not a priori a space-time here, only if you have a solutions to this, because these are gravitational fields, and gravitational fields describe space-time. Only after the solution can you construct classically a space-time. No? And you also have to choose lapse and shift, because they specify how your embedding proceeds. No? So this classical picture only comes after the solution, not before the solution. Right? Before the solution, this could be when you have a fixed background, but you don't have a fixed background here. And quantization, quantization then is like here. Here you get from this the Schrödinger equation, and here you get also a Schrödinger type equation. So quantization, I mean, then you have here the first derivative with respect to the conjugate variable, which is the x, and you can write this then in the form I h bar d psi over dx a is equal to ha on psi. Okay, the psi depends on now only on the physical variable. Also the same is here. Yeah, no, so okay, this is h bar over I, d over dx, and this gives a minus, and this gives then here hr. So you would have a Schrödinger type equation, also called local Schrödinger equation, because this is a functional equation and depends on x. So this is a local Schrödinger equation. Also called in field theory Tomonaga-Schwinger equation. Tomonaga-Schwinger equation. Because Tomonaga and Schwinger did that in the 30s and 40s. Actually, Stückelberg, the Swiss physicist, did it even before. So in principle, it should be called Stückelberg Tomonaga-Schwinger equation. I think someone of you asked me last time about the Schrödinger picture in quantum field theory. And in fact, in the early days of quantum field theory, people used the Schrödinger picture because they constructed quantum field theory in analogy to quantum mechanics, because this is what was known. And this is from these early days also known, this Tomonaga-Schwinger equation. Only later, when it came to the point that you basically had to do perturbation theory, then you had to develop Feynman diagrams and other tools. But this does not mean that the Schrödinger picture is wrong or useless. it's just not very useful for, say, the standard Feynman type of diagrammatic things. Yeah, this XA, okay, these are 4. This is not just one T like in here, because from the parameters here, you know these 3-dimensional surfaces you embed. And so you have here these 4. I mean, this is the 3 spatial ones, and of course the time into it. And this is why you have this local freedom to choose, say, your local time, whatever your local hypersurface. It's also called bubble time. I think Misner, Son, and Wheeler also use this term bubble time, Blasenzeit. So because locally, you can move the hypersurface here and there and there. So it's not a global shift of everything. You can do everything local because everything depends on X. Yeah, now we have advantages and disadvantages of that. And so I do this, and then we go to, in the rest of today, to B after that. So advantages. So I hope you can see this equation here. So the time, well, here time means these embedding variables, and the mini finger time, a bubble time, has been isolated, and also the physical variables. Now, so it seems that the problem is solved, that you can rewrite GR such that you can identify a time in this sense. So time, I mean, this means embedding separated from physical degree of freedom. Called here phi r or phi rps. No? So that in a sense, then, if you think about the linear approximation in gravity, where you have Minkowski spacetime plus something small, then you can identify, say, from this full formalism, the 2 graviton degrees of freedom which are under perturbation, and the embedding which is in the background. Yeah? Certainly there it works well, if you have such a picture. And of course, if you have this Schrödinger type equation, then this suggests, following Pauli, a natural Hilbert space structure. Because then you can say, Hilbert space structure integral psi star psi, and this depends only on this physical variable. And that's it, and it's conserved with respect to change of the embedding. If you go from one hypersurface to the other, it does not change. No? So, very good. So, natural Hilbert space structure. And with it, the probability interpretation of quantum mechanics. And this question with observables looks then very easy, because everything is an observable that just depends on the physical variables, phi, not on any embeddings or whatever. So observables are functions of phi and p, phi r and p. Okay, phi r and p s operator. Okay, so if you could use this and work with it and find interesting solutions and applications, that would be nice. But you already anticipate there are disadvantages that seem to overload this advantage. So the disadvantages, first, there is what one might call the multiple choice problem, because this canonical transformation here is far from unique. I mean, you can have infinitely many canonical transformations, and so we have infinitely many different variables here on the right hand side. So what is the correct one? Is there one distinguished one time? No. So this means this HAB PCD to XP phi P. I skip the indices, not unique. Okay, maybe you say that's certainly true, but maybe this is not an issue. Then, of course, you have this theorem by Torre, which is called the global time problem. Global time problem. A theorem that indirectly shows that this construction you cannot do on the full phase space. Full stop. No. You cannot have the space of all the H's and P's and find a global canonical transformation. So that's not possible. Yeah, so what is left is, say, some regions and some other regions where you couldn't do this separately. No, so this is what I already mentioned, this theorem by Torre. And then the third problem is called the HA problem. HA is this reduced Hamiltonian density here. That is, that you find by solving this. Okay, maybe you can solve the equation, but in general, this is very complicated. And because these things occur quadratically, and if you write it linearly, typically this contains square roots. Now, if you ever have thought in quantum mechanics a Hamiltonian that is actually a square root of some second derivative and so, then you are frightened immediately, no? Because to define this is a horrible task and not recommendable, and also destroys your boundary value problems and whatever, no? Because if you have a square root of minus Laplace plus a potential, say, then you have in principle all higher orders of derivatives, because you have to expand the square root, and I mean you cannot handle that. You know, so this means in general very complicated. No, square roots, etc. And also explicit dependence on the embedding variable. It's just as if you had in quantum mechanics something like square root of minus Laplace over to m plus a complicated function of t. No, and you would have to put this into Schrödinger equation to find solutions. I mean, that's hopeless. Okay, then also what we can call the XA problem. This I mentioned in words. These are the embedding variables, but they have this interpretation of embedding only after the classical equations are solved, because only then have you constructed your space-time in which the XA have this definition as embedding variables. As long as you have not constructed your space-time, you cannot talk of something being embedded in the space-time. So this means that this approach is misleading in the sense that you think about space-time and embedding and you have this Schrödinger evolution, but the point is you would first have to construct it. So XA are embedding variables only after the classical solutions are obtained. But these are the classical solutions. What about the quantum? In the quantum theory, you cannot do that. And in fact, in the quantum theory, there is no at that level space-time. I mean, I should say it again. I mean, if you have here HAB and PCD, they obey canonical relations. So HAB is a three-dimensional metric, and P gives you classically the embedding. So if they have a commutation relation, it means, according to Heisenberg's uncertainty principle, you cannot specify them simultaneously. But if you cannot specify, say, the street geometry and its rate of change, you cannot construct the space-time. As you cannot construct in quantum mechanics a particle trajectory. because for a particle trajectory you have to specify Q and P. No, the Q here and going in this direction, and then you have the trajectory. But according to Heisenberg in the quantum theory, I mean P and Q do not simultaneously exist. No, so there are no trajectories in quantum mechanics, but only wave functions. And so also here. So this whole intuitive picture, or what you think in the beginning would be an intuitive picture about space-time, breaks down together. So the next problem is called the space-time problem. Okay, it's related to that, but the point is one of these 4 embedding variables. Okay, let me give you the indices. Is the time t. You know? So t, and you have x1, x2, x3, the embedding time. But this should be a scalar. No? But if you have, say, here the picture of a hypersurface sigma and another maybe sigma prime, and they overlap here at the point x. So t would only be a scalar if it commutes with here the orthogonal transformations that go here, and here. No? So space-time scalar would have to obtain t of x commutes with the integral of the normal part of the Hamiltonian, and here the lapse function over sigma. But this is in general not the case. I mean, this depends in a complicated way on all the variables, and except maybe for very special situations, in general this does not commute. So you can construct an embedding time, but it's not a scalar in this sense. Yeah? It's a very strange quantity that you do not know what it really is. So in general, violated. In general, violated. Yeah, there are other things like anomalies, quantum field theoretic anomalies, for those of you who have heard that in quantum field theory, and also the construction problem that this deparameterization, also called reduced quantization, can only be explicitly done in very simple situations. For example, gravitational waves is one of them. When you are on linearized gravity, when you're very close to Minkowski space. Also some spherically symmetric situations where you can exploit the symmetry. There you can do it. But if as soon as it becomes more complicated, then you run into these disadvantages. I mean, that you get very complicated H's. Yeah, you had a question? This is true, it's a good question, yeah. So that you would only allow some. As far as I know, there are no theorems available. It's just that whenever, also in these examples, you construct something, what you get violates that. So you would really have to prove a theorem that gives you a certain restricted class, but which seems in some relevant cases to be useless. There is one example, maybe because you asked the question. So one rather well-known example where you can, in principle, do that is the following, where you can use Yoick time, so-called Yoick time, or extrinsic time. This is one of the few things that you really read about in the literature. There you can construct such a T x of HB PCD, which turns out to be 2 over 3, and you have the square root of the determinant of the 3 metric PCD HCD. So this is, you can also write as minus square root of h over 8 pi g times the trace of the second fundamental form. And the conjugate thing is just minus square root of h. So you can solve these constraints in this way by choosing, so to speak, the canonical transformation such that you have this t. Unfortunately, so this has very nice properties to some extent, but it's not a space-time scalar. So this here is the York time. Here, it's York time basically is the trace of the extrinsic curvature. Yeah. In cosmology, that's the Hubble parameter. There you have a nice intuition. But this is not a space-time scalar. So this is why I think people have not thought much about theorems that find it. But if you have this, if you choose this as your time, then I mean then h orthogonal equals 0 can be written as a pt plus ht equals 0 with a true Hamiltonian, which is integral d3x square root of h plus, okay, one does not do it for the momentum constraint. So they remain unsolved here, but this first constraint, one of the four, is solved. And of course, this is just a three-dimensional volume. So this true Hamiltonian, if you forget about that, has a nice interpretation. It's just a three-dimensional volume that somehow propagates you. No? And this is why this, and one can prove that this has a solution. Yeah? I mean, mathematicians have proven that you can solve that. And this has some nice features, no? Because you can say the volume is the one that is the Hamiltonian, such a three-dimensional volume. I mean, you can make an energy out of it if some variables, but it's definitely not a space-time scalar. Now let me go. Therefore, now I spent much time on this, but the summary is that this is worth to try. We know that it cannot be done globally, but we can do it for certain models, and it has been done in the literature by Karl Kukash and others. Models like spherical symmetry, cylindrical symmetry, and things where symmetry is so big that you can somehow solve these equations. Okay, so what is the alternative? I mean, if you cannot do it in general, I think at the end we are not happy just doing some simple symmetric cases. We want to have a general formalism. And so the second thing is then here the choice of a concept of time after quantization. So we then really follow or apply Dirac at the very beginning in the original form of the constraint, without first bringing them or squeeze them in such a somewhat arbitrary form here. So not squeezing them classically here, but just take them as they are and quantize directly. So that's then this option B. And so we have these commutation relations here. So this we substitute by, as I've written down earlier, maybe it's erased, but by multiplication, and this by h bar over I differentiation. So so we have then h orthogonal hat on psi equals 0 and h a operator on psi equals 0. No? And I have given you last time the explicit expressions of them, and so you must take these expressions, substitute h just by multiplication and the p's by differentiation. And then you get the following. I mean, from this you get then minus 16 pi g h bar squared times g a b c d d squared over d h a b DHCD minus square root of h over 16 pi j 3r minus 2 lambda und psi equals to 0. And this here is simpler, minus 2 dB h AC h bar over I d psi over d HBC is 0. This is the vacuum case. Now I will in a minute add also the matter parts. Yeah, so that are then the equations. No? So without solving them or trying to solve them, to put them some linear p occurs quadratically, and this is why here these things are quadratic, like in the Schrödinger equation. In the Schrödinger equation you would have here minus h bar squared over 2m Laplace, no, plus potential on psi. Okay, that would be then an energy here. Okay, this first equation is usually called the Wheeler-de Witt equation. In some few papers, all of this is called Wheeler-de Witt equation. Okay, but usually it's the first equation. So John Wheeler, no, the one from Misner, Son und Wheeler in 1968, and Price de Witt, 1967, they for the first time discussed this. I mean, this thing was written down earlier, in fact, by Dirac in 1958, but Dirac stopped there. No? He discussed the classical version, and then he said at the end we should do that, but he did not discuss them further. And 1958, and Wheeler and de Witt took it seriously and wrote it down explicitly and discussed it, tried to solve it, and things that we do also now. Yeah. So in the first years, of course, after this was done, it was not yet called Wheeler-de Witt equation. So it was actually called sometimes Einstein-Schrödinger equation, because this is a quantum version of Einstein equation, so in a sense a la Schrödinger. But as Karel Kuchasch remarks, so in 1973 he wrote the following: the quantum version of the super Hamiltonian constraint, this is also the super Hamiltonian constraint, the quantum version of this was called the Einstein-Schrödinger equation by John Wheeler, and the Wheeler-de Witt equation by others. Because I cannot recall any other physicist who would more strenuously object to the idea of quantizing gravity than Einstein and Schrödinger, and they two were not in favor of quantum. And because I am not John Wheeler, I shall use the second name, Wheeler-de Witt equation. So this is why since then it's called like that and not Einstein-Schrödinger equation. I think that would be confusing, Einstein-Schrödinger equation anyway. Okay, so this often we write here also quotes because of this so-called factor ordering problem, because classically this is just the momentum squared, which is a function. But I mean, whether you put this also depends on the ages, if you recall. So it does give a difference if you put this here in front, for example, because then it hits this and gives also first derivative. That's the factor ordering problem that you have here, and that we will encounter later. Factor ordering problem. So this is done here by just these quotes. And of course it means there are some regularization needed because there are some delta functions that diverge and so on. So this is of course an issue to be discussed and solved. But of course if we have this, then we just have equations h and psi 0. So definitely there is no time here. And we will see then 2 weeks the timeless options that only the semi-classical time exists. So from this we can derive a semi-classical time as an approximation. So Schrödinger equation in the functional form, in the quantum field theory form, will come as an approximate equation in certain situations. So that certainly is okay, but not in general. So we wonder what we do in general here. And because the choice of time is also related to choice of Hilbert space. Let us have a brief look at this. So what do you use in quantum mechanics? You use what is called a Schrödinger inner product. This is the L2 norm, integral psi star psi. So you have, so the question is about Hilbert space and about time, so to speak, which is related. And we have the option first, the so-called Schrödinger inner product. So you say, yeah, we just write down what Dirac wrote down with Bra and Katz. And we say, okay, we integrate now over all three-dimensional geometries, which is Riem, sigma, Riemannian matrix on sigma. These are all the HABs that are in that manifold with some measure. And you have then, okay, the usual. Okay, this is very formal. We have to go to the mathematicians to that they educate us about maybe Lebesgue measures and all that, what you can do. In fact, a Lebesgue measure cannot be constructed for quantum field theory anyway, but you can write down some formal measure, of course. Now, that looks fine maybe at first glance, but notice that you integrate here over all the variables. Now, this is not what you do in quantum mechanics. No? In quantum mechanics, you integrate at d3 and x, and then you have psi star psi. But psi depends on x and t, and psi of x and t. So if you integrate over everything that is in the argument, then it would mean you integrate also over t. But because without the integration over dt, this is a constant, integrating over dt just gives infinity. So then the danger would be if you do that, you just get infinity. It's not so simple because this does not play the role of time, and of course it depends on really the dependence on that. It could be that you can make a virtue out of that just by restricting to wave functions where this is finite. This could be, and in quantum cosmology, which we will discuss later, this is possible. So finiteness as a criterion. Perhaps there are some additional boundary condition that we are allowed only to use wave functions that solve the constraints, of course, and which lead to a finite scalar product. But even if this holds, what about the probability interpretation? That's the probability that you find on the three-dimensional space the certain three-metric configuration. But usually probabilities are then evolve in time, and you have unitarity, but there's no time here. So who has the time? Who measures probabilities? No? So that's unclear also here. Probability interpretation. So this is why some people, in fact, David did this in his pioneering work of 1967 to suggest another inner product, and this is known as the Klein-Gordon product. I mean, the Klein-Gordon equation, I guess you know, D'Alembert minus m squared on phi is equal to 0, which was a candidate equation for relativistic quantum mechanics. And there is another scalar product that is conserved for the Klein-Gordon equation. And David argued, because this here is indefinite. I hope I mentioned it last time, otherwise we have to discuss it again. This here is has signature local of minus plus 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 plus. So this here is not really a Laplacian but a D'Alembertian operator. So there is one degree of freedom here in the HAB that has the wrong sign. And so it looks like an oscillating string equation or so. And then you can say, no, it's not like Schrödinger. It's like a Klein-Gordon equation. And we can use the Klein-Gordon inner product. No? So this is GABCD is indefinite. So analogy to Klein-Gordon. No, this is to Klein-Gordon equation. And David showed this explicitly, so maybe I don't need much space. I will just maybe allow myself here just to use this space here. So David in 1967, so he made instead of HAB use HAB tilde, which is defined as the determinant, the minus 1/3 times HAB, and use the square root of the determinant, because this is this has just determinant 1. Because determinant of this is determinant of this times determinant of this. This is just h, and this gives you then the power 3 because it's 3 dimensional. So h to the minus 1, and so this has determinant 1. And so this is fixed, and so you have separately a determinant as a degree of freedom. And then he could write the following form of the Wheeler-DeWitt equation: 6 pi g h bar squared square root of h d squared over d square root of h squared minus 16 pi g over h bar squared over square root of h. Then we have h ac tilde h bt tilde d squared over dhb tilde dhc tilde minus square root of h over 16 pi g 3r minus 2 lambda applied on psi, which now depends on square root of h and HAB tilde equals 0. So you see, if you compare it with that here, instead of all the HAB, you split them up into this HAB tilde, which is the conformal part. It's just the shape part, and the size part, which is the local determinant, the local volume. And so here, instead of that, I mean, the other equation is unchanged. It's only about the Wheeler-DeWitt equation here. And you see here that here you have a plus, and here you have a minus. And one can show this is positive definite here. Okay, I have not shown, but that's what David also showed here. That's positive definite. So that is, so to speak, minus Laplace, like in the Schrödinger equation. But in addition, you have this here. And so it looks, with the other sign, looks like this local square root of h is a kind of intrinsic time with respect to the equation. So square root of h is a local intrinsic time. So this would be a time after quantization, that you only have the 3-dimensional volume, but you can construct a time out of this. And this is square root of h. And here we have also seen here in this case also square root of h plays the role of, it seems, also the true Hamiltonian here. So this volume has some kinematic features, it seems. Square root. So I hope it's clear that you have here really two different signs. Positive, so these are all these 6, no? HAB are 6, so these are 5, and this is 1. So the 5 are here, and this gives you a positive definite expression, like a minus pi squared over 2m. And the 6th is the local volume, which has a different sign. And because of different signs, so David suggested, yeah, like the Klein-Gordon equation, then we integrate in the scalar product only over those. No? And formally, it's independent. You can show independent of square root of h. So in Klein-Gordon equation, you have an inner product that defined on a spatial hypersurface. And you can show that if you go in time forward or backward, it does not change. So it's time independent. And you can formally, if you don't mind about all this functional derivative, formally show here the same. So why not using this? And so these are the two options. And yeah, I mean, the Klein-Gordon inner product, of course, has these disadvantages that you maybe learn when you learn about relativistic quantum mechanics and why the Klein-Gordon equation is not a fundamental thing. You know, it has these positive and negative frequencies, which you avoid with some of these difficulties you avoid when you go to the Dirac equation, but this is not an option here. No? So these positive negative frequencies, so this would mean that the probability interpretation is unclear, because it would be, say, for a real wave function, would just be 0, you know, and so on. So it's not so clear. So Klein-Gordon inner product conserved with respect to square root of h, but is not positive definite. So is this a disadvantage? Yeah, that's what many people said, because then they say you cannot make a probability interpretation. But the issue that we also discuss next time is whether we need a probability interpretation in the full case at all. Yeah. So the point is we need it in the semi-classical limit, but there we will see that the standard formalism comes out. No? So is this really something negative? I mean, in relativistic quantum mechanics, then you argue that okay, Klein-Gordon is not sufficient. We go to quantum field theory because we have this particle creation and all that, and we cannot just have a mechanics as a quantum mechanics of special relativity. So some people have argued here the same. So they went to a next order quantum field theory, so making this wave function again into an operator, which was then called third quantization. But I will not bother you much with third quantization, because this was discussed in the 1980s and 90s, but at the end I would say that this is nothing that has been established as an alternative. Although it would be just one-to-one to what you do in quantum field theory. So the last thing I just say in words here, a similar calculation I have already done in chapter 3 is the interpretation of this equation. And I think I already mentioned that Peter Higgs, who became later famous, of course, with the Higgs particle in 1958, had a short paper on that. Okay, so this equation was done before Wheeler and DeWitt. No? So that, I mean, Higgs, this was the same year when Dirac wrote down these equations. So he showed that this has the interpretation that psi does not change if you change coordinates on the 3D-dimensional space. Now, I showed it in chapter 3 with the parameterized field theory, just making a Taylor expansion and a partial integration. And so psi does not change, at least not under coordinate transformations that are connected with the identity. If they are not connected with the identity, it can get a phase, a so-called a phase. A phase is possible. I do not know whether some of you have heard from quantum chromodynamics or so. There are some theta vacua and some states. Something similar can happen here, but we will not discuss this. So that's the first part of chapter 5. In the second part, in 2 weeks, we will then start from this and show you how we can go back to getting time and the limit of quantum field theory in a fixed curve time, and also mention possible observational effects of that before we then go to black holes and to cosmology, where we then apply this equation in some models. But there may be questions. Yeah, if not, then please come also next week to Tadevik's talk, and we will meet again then in 2 weeks. See you.